So that's just to let you know about those new rates which will become effective from August. I'll tell you what events we've got coming up. Forthcoming meetings, Winchester Weekend, very popular, exciting event, Friday the 12th to Sunday the 14th of April. Bookings have now closed. However, if you want to come just for a day, just for the Saturday, you can just turn up. You won't. We can't book you lunch because the venue wanted the figures for the lunch already. So, but if you bring sandwiches, you can just turn up and you could attend because we are not at capacity for the actual lecture hall. And I will be chairing a meeting of the equipment and techniques section, which will occur at the Winchester Weekend on Saturday, starting 14:30. So you can just turn up for that if you just want to turn up for the afternoon, and there will be no charge. On Saturday, the 11th of May, we are holding a whole day meeting in Greenock near Glasgow, and the topic of that is the music of the spheres. And we've got some very distinguished speakers, including Dame Jocelyn Bell-Burnell, the discovery of pulsars. So that should be very good. That's in Scotland on 11th of May, and you can book for that on the website. Also in May, following Saturday, Saturday the 18th of May, Historical Section is holding a meeting in Ipswich, 10 o'clock in the morning to 1700 in the afternoon, and you can also book through that. There's no charge, we just want to know the numbers. So I think there's no charge, we just want to know the numbers. So you book on that through the website. And then the next meeting we are holding here at the Institute of Physics will be on Wednesday the 15th of June, when we will have talks from Bill Leatherbarrow, Peter East and Tim Parsons. Today we have two talks from very long-standing BAA section directors, the director of the Mars section, Richard McKim, and John Rogers, director of the Jupiter section. And as you see, we've got a lovely orange glow bathing us from the Martian atmosphere. So I will now call on Dr. Richard McKim to tell us about current BAA studies of Mars. Richard.
Thank you very much, David. It's a pleasure to be here and to give you a talk about Mars. I'm going to be talking about some of the research we've been doing in the past few years. And quite often in the past, I've talked about dust storms on the planet. I'm going to talk more about white cloud behavior this time, and also give a preview of the next opposition. So let's begin. This is just a reminder to show you that Mars is intermediate in size between the Earth and the Moon. And I've put down here some maximum and minimum temperatures. So with the Earth, we can see there's a huge range of temperature, and the mean is about 14 degrees C. The mean for Mars is minus 63, more than a little bit chilly, and therefore will be very largely effective in controlling the meteorology. We also have a much smaller mass and a greater distance from the Sun and a much more elliptical orbit than the Earth. So all of those factors are important in understanding Mars. And I can verify, I did some original research the other day to verify that the average temperature of the Earth is indeed 14 degrees by visiting Hunstanton, where it was indeed 14 degrees C all day. And I have to say that if I was to repeat this experiment in the summer, the temperature is still 14 degrees C. Not as bad as Skegness, you'll say, where it is probably like the Martian mean of minus 63. The difference on Mars, of course, is that the tide is a lot further away. There are no shells to pick up. There's a terrible problem with dust, and it's not very warm. But other than that, probably very interesting to go. What I'd like to perhaps start with is to just show you the enormous difference in the resolution of images, telescopic images and photographs, if we compare the planet over the course of the last century. So let's start with a little comparison. And here's a comparison. This is a photograph by Barnard with the 40-inch Yerkes refractor. The best he could do, 1909. Cutting-edge stuff for the time. Then there was a series of red, green and blue Mauna Kea photographs here, and this is a colour composite by Manos Kodasis, who has turned it into an actual colour photograph. That's a dust storm on the right of the image there. And compare this with an amateur image with a much smaller telescope by Damien Peach, 2022. So the thing that I'd like to say here is that a lot of the phenomena that we can see today with our backyard telescopes were considerably beyond the range of the people who went before us. And that sort of divides some of the periods of Mars observation somewhat like this slide. So if we go right back to the beginning, if we want really reliable observations, of course we would like something impartial like a photograph or an image. Very first successful photographs of Mars were taken in the late 1880s by W.H. Pickering at Arequipa in Peru. The systematic photography of Mars began in 1905 with the work done by Lampland and Slipher at the Lowell Observatory. And if we go on ahead, what about amateur photographs? Well, amateur photographs of Mars did happen in the 20s and 30s, but they weren't very common. They were taken on very grainy film. And the first really successful amateur colour images date from 1954. If we go still further ahead in time, we come up to the 1980s. One of the things for those of us who lived through that period was the use of the TP2415 film, which was a very sensitive film, but also a fine grain film, which was very good for high resolution amateur planetary photography. So in the Mars section, from the early 1980s, we began to get high quality photographs, but of course no CCD images. That we had to wait to the late 1980s, early 1990s, and then 2002, the webcam revolution, as it's been called, where we had software for the stacking and sharpening of images, so we could get these super fantastic results that have become almost the norm today. So what I'm going to do, I'm going to talk some examples of different parts of the planet and talk about some of the research that we've done. And one of the things I've done, based on that last slide, is to go back to the beginning of the webcam revolution and to analyse all of the reports that I've done in that time and look at the dates of seasonal phenomena, how constant they are, how variable they are, and to give a description of some of the things we can see. And polar caps, so that's the next thing we're going to talk about. Here's a picture from the Hubble Space Telescope from 1997 showing the winter cap on the left, a swirl of dust over it as well. And then finally the summer cap remnant, the little remnant of water ice that never completely evaporates during the summer of the northern hemisphere. And that very dark belt of what are in fact dunes around the North Pole. I'm going to go on to show some amateur pictures here. So on the top slide, I've got two pictures showing the decrease of the South Polar Cap, and you can see the enormous range in size of the South Polar Cap. And on the bottom slide, on the left-hand bottom one, we've got some images showing the cloud canopy over the fresh spring cap. You can just see that separated from the hood. And then we can see the summer remnant several months later, and a lot of clouds in the Martian atmosphere. So obviously, as the polar caps wax and wane, so the content of volatiles in the Martian atmosphere change, and we're largely concerned with water ice, of course, in the amateur observations. And for any chemists in the audience, and I know there are a few chemists, Jeremy Shears, chemist, I'm a chemist, and it always reminds me of an apparatus called the cold finger apparatus, which was a way that chemists use for purifying substances. And basically what you do is shown on the next slide. One of the ways in which you can purify something in the lab is to make it sublime at reduced pressure. Now, sometimes you want to purify something by distilling it, but a lot of substances will actually start to decompose at their boiling point, or in certain cases explode, which is one of the fun of being a chemist. What we would probably like to do is to avoid that if at all possible. And so what we do is we do low pressure, and this normally causes the substance to sublime. and we can do that. And of course, this mimics what's actually happening, this transfer of vapor between one cold pole and a warm pole of the planet. So what I'd like to show you in the next slide is how a chemist would mimic the atmosphere of Mars. So number 1 and 2 there is a test tube with some cold water going through it. Number 3 is where you attach the vacuum hose to your apparatus, probably a water pump or an oil pump going down to a few millimeters of mercury in pressure. Number 6 is where you put the substance that you want to sublime. Number 7 is where you put the electric heater or a Bunsen burner if you're feeling lucky. And number 5 is where the vapor will sublime and be purified. So this is exactly what's happening with the poles of Mars. And from the internet here's somebody looking at some camphor. And at the bottom there you can see the camphor. It's being heated on the gauze, and it's subliming and collecting around the cold finger. And I think white substances turning into white substances aren't very interesting photographically. So here's some with some iodine, which is much more colourful. And this is one of the things why chemists like chemistry so much, because there are lots of pretty colour changes and, as I say, quite often explosions as well. There are no explosions on Mars, though, as far as we know. So this is the sort of seasonal phenomena that we can see. Here's a series of drawings, not images this time, made by me, 2022. The first one at the top, we're going to have south at the top for this part of the meeting. John will have north at the top for his part of the meeting, so you'll all have to stand on your heads for that part of the meeting. But south at the top, good old British fashion for this part of the meeting. So the South Polar Cap in early spring at the top there, going down to a very small hazy remnant in the last drawing. And as time goes on, a brighter and brighter area of the North Polar Hood forming along the north limb. So this is the usual progression of seasonal events. Just to show you some more pictures, these are spacecraft pictures this time of the North Polar Cap, the South Polar Cap. We can see these grooves in the polar cap. This is some sources I've read describe this as being due to the spiral patterns of winds that form over the polar caps. Maybe that's correct. And we can see the South Polar Cap, they're smaller than the North Polar Cap summer remnant. So like the southern counterpart, the North Polar Cap reaches a summer remnant stage, and this seasonal date is relatively fixed. And then, as I said, clouds form around it and finally form the hood over the cap, which deposits the solid H2O and CO2 ready for the next season. And I'm going to show you a series of drawings. What does it look in the eyepiece? So here's some drawings from 2016 that I made, and we can see at the top in A and B and C, we can see a relatively small northern polar cap at the bottom there. In D, we're starting to get some wider cloud formation forming. Sometimes you see the cap again, as in E, and then in F, we've got the hood again. And we have a series of clouds which unite together eventually to form a continuous hood over the pole. And when we see it again the next season, we see the fresh polar cap. I thought it would be interesting to compare some data, and this figure LS here, the areocentric longitude, is a measure of the position in the Martian year. I'll introduce it formally in a few minutes' time, but just to give you an idea that it's not quite the same all the time. If we look at 2001, we can see that the polar hood in the north began before the hood dispersed in the south. So we have a period of time when we might see both poles covered in vapor, and the period of time for which this happens does vary slightly from Martian year to Martian year. And we think one of the reasons for this is probably that these processes of deposition and cloud formation are extremely sensitive to the temperature of the Martian atmosphere, and thereby the dust loading of the atmosphere. If you have a tiny amount of dust from a dust storm injected into the Martian atmosphere, it increases the way in which the atmosphere can absorb heat, and it will change these data in a small but subtle way. And now to introduce the Martian years. I think I've shown this slide before at BAA meetings, but the audience might be different. So What we've got here is the Sun in the middle, as it usually is. After that, we've got the Earth, then we've got Mars. You can see the Martian orbit is very elliptical here. The closest point to the Sun is marked P at the top of the diagram, that's perihelion, and bottom aphelion. And these, we can imagine a 360-degree protractor laying on the screen here, and the areocentric longitude is defined to be 0 at the beginning of northern spring, or if you like, southern autumn. And then the seasons follow 90 degrees apart. So northern summer begins, LS 90, northern autumn, 180, and so on. And the dates of perihelion and aphelion are given at the bottom of the slide. Now we know that there is a cycle of some 15 or 17 years over which Mars and the Earth come to the same relative positions. And we can see that on this slide here, you can see around the edge of it the dates of past oppositions. And I've gone from 2010, 2012, 2014, etc., round to 2022, and then finally 2025, which has been highlighted. And oppositions are classed as perihelic or aphelic, depending on whether they occur within 90 degrees either side of the date of perihelion. So the next opposition, 2025, unfortunately, the opposition is going to occur in January. That's not very good. And also not very good, it's going to be a long way from us. So there's a seasonal similarity between 2010 and 2025. So if we go back to the 2020 report of the Mars section, which you can have a look at on the website, all of the past reports back to 1892 are on the website, you will find that gives us a good guide as to the sort of phenomena and the sort of images we'll be obtaining in 2025. If you want a better accord, and there are people who spend their lives looking at what would the best possible agreement be, and if you take an interval of 32 years, that's a little bit closer. 47 is better still, and the best one I can give you is going back to 1898, but what I can't show you is any CCD images from 1898, but I could show you some original drawings. That's an interesting historical comparison. And let's have a look at some actual distances here, and because I stole this from the internet, from an old publication, they're actually in miles here. I'm sure most of the audience, though, still think in miles, so that's all right. So we can see that the biggest distance there is about 62 million miles, and the shortest is about 40 million miles. And this is a cycle of oppositions from the 1960s to the 1970s shown in this picture. And we can see, again, how elliptical that Martian orbit is. And it's always been a great regret to me that when Mars is at its closest to the Earth, it's in high southern declination. So the only consolation that we've got as observers living in a north temperate latitudes, as we do in Britain, is that at least the planet will be a long way above the horizon in January next year. So I'm hoping many of you will observe it. And perhaps I should just ask, would you like to, as a bit of audience participation, could you put your hand up if you looked at Mars at the last opposition? Or ever in the past? Amazing, that's almost everyone here. And the others who didn't put their hand up, why not? See me afterwards. Now, one of the things that we do in the Mars section is we measure images. Maybe this is because we don't have any other hobbies. It is rather onerous thing to do. But for those who are mathematically inclined, here's a nice image. It's a Hubble Space Telescope image. There's a little black dot in the middle, which I'm going to call O. And we measure the distance OX and OR, OR being the radius of the image. And if you take the inverse sign of OX over R, that gives you the apparent latitude of the south edge of the North Polar Cap. Now, this would be the latitude if the Martian equator was at the center of the disk, but quite often one or other of the poles is tilted towards us by an amount called in the handbook DE. And this is the latitude of the center of the disk of Mars as seen from the Earth. Okay, so, or the latitude of the sub-Earth point, if you like, and that has to be added to get the true latitude. Now, we get sent in about 10,000 images each Mars opposition, and those in red light are very suitable for measuring the cap because overlying hazes don't show up in red light. And I suppose that of the images shown that we get in, about 2,000 of them are suitable for measurement. So the next thing to do is to get all of the images on the laptop and to measure all of them. And this does take more than a little while. It takes me several days, if not a whole week, to do that. And so you measure at 1,000 to 2,000 images, and then you average them together in short intervals of LS. I tend to take about a week, which is about 5 degrees of LS or so. It's also possible with the southern cap, which becomes rather asymmetric as it shrinks. You can measure the diameter in the east-west direction instead of the north-south direction. And what method you choose depends really on the presentation of the planet to the Earth. Sometimes we have to contend with the phase of the planet, cutting off part of the polar cap, so one method might be preferred to the other. And having made those 2,000 odd measurements, we get something like this, which we call a recession curve. And we're plotting here the latitude of the polar cap against time. The upper curve is for 2003, and the bottom curve is for 2018. I haven't gone before 2003 because before that time we have to rely on photographs and drawings rather than on the all-powerful CCD image, which is a really accurate way of doing it. And we can see that these curves, with the exception of the first few points, are almost exactly the same, which shows that the Martian seasonal cycles are almost precisely recurring. What's very interesting, though, is the 2018 points which lie below the other curve. And what happened at this particular stage, there was a global dust storm, and some dust very quickly fell out on the polar cap. Now, I don't know about you. If you want to clear snow from your driveway, I normally use a shovel, but you might be one of those persons who takes soot and puts it on the snow, and then goes back inside and waits for a week. And the soot, of course, helps the absorption of sunlight, if there is any, to melt the snow. And this is basically what's happened with the Martian polar cap. The dust has fallen out on the polar cap, decreasing its albedo, absorbing more solar radiation, and then after a period of enhanced recession, the two curves catch each other up again. So that sort of thing is very interesting if you've got plenty of data. We can also see that as the caps shrink, they exhibit bright spots, they show rifts, detached parts, and sometimes, because there are often winds blowing off the cap rather than onto the cap primarily, we see quite a lot of points where dust storms are generated at the edge of the cap. And we get seasonal fragments which come off at particular dates, and the appearance of those is a way of actually seeing whether some of the historically observed oppositions were following the same sort of rule. So here's a comparison on the right-hand side, a drawing I made showing a detached portion of the cap, shown with the arrows there, called Novus Mons. But originally these were called the Mountains of Mitchell. They are believed to be mountains, and they were discovered by a chap called Mitchell. And there it is. There's the discovery drawing from 1845. And Ormsby McKnight Mitchell was an American who founded the Cincinnati Observatory. I think it's a 15-inch refractor. Nice way to observe. And he has this discovery drawing showing part of the polar cap split off. And the date at which that occurs is very, very reproducible. He was also a general during the Civil War who happened to have the fortune of being on the right side, which is always very helpful. Let's have a look at some of the dates. So 1988, LS239, and we can see here that it doesn't vary very much. 2016 is rather approximate, weren't enough observations. We can see that there is a slight variation, but not very much. And just to sort of digress, which I like doing, Mitchell's sketch actually highlights some of the problems in interpretation. If he's got the pipe bowl of the sinus sebaeus in the right place, he's got the polar cap in the wrong place. It should be a few degrees to the right. And I can also tell that he spent a long time over this drawing, because B, which marks the position of the Syrtis Major, that should really be beyond the limb. So I think he spent over half an hour on that drawing. And I think he started on the left and worked his way to the right. It's still a fantastic drawing from a historical point of view, but it does highlight some of the problems we have in using drawings instead of images. I'm going to talk about something now called the Equatorial Cloud Belt, or the ECB. And this here is a Hubble photograph from 1997. It's a whole planet map, south at the top, north at the bottom. And you can see this bright tract of cloud along the equator. And this is an image taken in the near UV, 410 nanometers. And we can see some landmarks here. For example, at 270 at the top there, you've got the Hallis Basin. And we can see some of the Tharsis Montes on the right-hand side between 90 and 180 degrees. We can see this broad band of cloud completely covering the Martian equator. And this does happen for a large fraction of the northern spring and summer seasons. And it's always nice to see and to time it. And I've got here some marvellous images by the late, great Don Parker, who many of you will remember as being one of the absolute legends in planetary photography. And what I've got here, I've got some red light photographs which don't show it, and some blue light photographs which do, and a few UV images on the right-hand side that show it even better. And I would just like to say to imagers, it's really good to have red and blue images, but if you can do some ultraviolet images, you'll be providing even greater value for science if you can do this. Much more difficult to do, but if you can do it, please do try. And we can see on the first pair of images, on the blue one, you can see an east-west elongated belt of cloud over the Chryse-Xanth area, desert area, just north of the Valles Marineris. And we can see how this belt changes with time. It's sometimes broken up into smaller bits. Sometimes it's continuous. And we can see that by LS 96 at the bottom of the first column, it's a really continuous and really bright band showing up in the blue light images. And if we look at another hemisphere of the planet, we can see the same sort of behavior. The equatorial cloud band tends to be broken up a bit by the Tharsis Montes because they poke up through the cloud deck. And again, if we have a look through the archives, which is what I've done before preparing this talk, we can see that there are small changes. It tends to begin in part about LS1, right at the beginning of northern spring. It's complete at about 45 degrees, and it's last complete about 145, and then it breaks up into patches and disappears. So again, I think what's really important here is it's comparing the dust loading of the Martian atmosphere. If there's a bit of dust in the Martian atmosphere, it's going to change these dates in some way. So very interesting to try to get those timings each year and to make comparisons. Now, these modern observations at high resolution have also explained one historical puzzle, and that was the seasonal colour changes of the planet. I don't know how many people have ever seen the classic books by Percival Lowell. Mars, Mars and its canals, Mars as the abode of life. No? Well, if you have, there are some lovely colour pictures in there, and Lowell said that at one time of the year, the Syrtis Major, the really dark feature that even beginners can draw on the planet, is a robin's egg blue. Now, in fact, we know that in reality, the Martian dark patches are really more or less a neutral colour. They don't really show much true colour at all, but there are certain times of the year where they appear bluish. And on the other hand, the markings to the north of that, which would be Utopia on the IAU map, tend to appear neutral or perhaps slightly brownish. And what we know now is that, in fact, what's happening when Lowell saw that intense blue colour, I think it's perhaps quite well shown on the second picture there from the left, where the Syrtis Major is seen near the morning terminator. This intense blueness is due to the presence of the equatorial cloud belt. And what Lowell thought he was seeing was seasonal changes. He thought he could see the vegetation dying and a colour change, and then seasonal renewal. Now, the Martian colour changes are, of course, very complicated because there's subjective colour contrast here as well. If we take a grey patch and put it onto an orange ground, that grey patch will appear slightly bluish because the eye-brain combination gives it a subjective bluish colour. But here's a real bluish colour, but it's due not to colour contrast, but to the presence of this scattering belt of white cloud, which is causing the short wavelength, the blue end of the spectrum, to be scattered more than the rest. And so whenever the equatorial cloud band is thick, we see this bluish colour to the Syrtis Major, which happens to be the only marking that crosses the equator and has the right latitude. Okay, let's go on to the Tharsis volcanoes now. These will be well seen in 2025 for those of you who get the telescope out. And we'll start with a mountain, which I could almost say this was my picture, except that I was too lazy to find my own picture of the Matterhorn when I've been there. And we see this banner cloud going behind the Matterhorn. And it's a really fantastic phenomenon to see if you're in that part of Switzerland. And what I've done, I've stolen a series of slides from a video on the internet, and we'll just have a look at the way in which the cloud develops. So I'm just going to go through these one after another, and you can see that a cloud forms in the lee of the mountain on the left-hand side, and these clouds are forming because the moisture-laden air is going up the sides of the volcano, and as of course it rises, it cools, and the water vapor condenses to form these clouds. And we see this phenomena also on Mars. So let's have a look here on the next slide. And by the way, the Matterhorn is not the only Earth-based mountain that does it, but there aren't that many that do. So on the planet Mars, we've got the Tharsis Montes, which lie on a bulge which is several kilometres above the rest of the terrain. At the top, we've got Arsia Mons, Parvonus Mons, Ascraeus Mons. And to the right of them, we've got the letter O, which marks the biggest volcano so far in the solar system, Olympus Mons, which has a caldera approximately the width of the Hawaiian island chain. We've also got Elysium Mons on the right, and we've also got Alba Patera, which is towards the north. And all of these have different seasonal characteristics. Let's introduce some of these. So Arsia Mons is the highest of the Tharsis Montes, and what's most important for the banner cloud effect is that it's isolated from the other peaks. If you go to the northern one, Ascraeus Mons, then Olympus Mons isn't that far away from it, and it's perhaps not quite as isolated as Arsia. And we know that these are fantastic heights with the lower gravity of Mars, absolutely fantastic heights for mountain building to occur. So they'd be really spectacular if we could see them. We can, of course, see them from space. And here's an image. I think this is the only image I've seen from the HOPE mission. This was the Saudi Arabia mission to Mars. And this lovely one we can show on the bottom left there, Olympus Mons. And on the right, we can see the Tharsis Montes chain. And I'm not sure whether this is an evening or a morning shot, because it didn't say on the website I got it from, but it could have been either. There's another lovely picture there showing the cloud in the lee of Olympus Mons at the medium left. Okay, we can also have a look at these from the Hubble Space Telescope, and I said I was going to have south at the top, so I'm going to turn that upside down. Shouldn't really have shown the last slide at all, should I? So we've got the North Polar Cap at the bottom there, and on the left-hand side, we've got the evening limb, we've got the morning terminator on the right. Some other interesting things we can see. On the left-hand picture, we can see an evening cloud over Elysium Mons, and these clouds do tend to occur in the Martian evening. Sometimes they begin to form at noon, and they get brighter and brighter and more dense as the afternoon goes on and the temperature goes down. We can also see, incidentally, some frost in the Argyre Basin, and some of the best images, for example, Damien and others, have actually even seen some of the outlying craters around Elysium covered with frost, and this is really high-resolution stuff. Now, on the right-hand slide, I've marked the position of the mountains, and there are little clouds visible over them, which would be larger and denser if that picture had been taken a few hours later. Okay, so it's interesting to have a look at the seasonal dates, because if we know the seasonal dates, we can predict precisely at what times these clouds will appear in the forthcoming opposition, which, by the way, has already begun. So I've got here some dates for you for 2010, and Arsia Mons, which is the furthest south, the cloud there starts at a much earlier season than the ones at Pavonus and Ascraeus. And I thought it would be interesting to compare it with 2007. because the Martian weather, although far more predictable than that of the Earth, is still not quite constant. So we can see a small difference there in the dates, the seasonal dates at which those clouds begin. I haven't given the termination dates. I'm not going to bore you with lots of numbers. So I'm going to say that the main reason they last for different periods of time is primarily the difference in latitude. Of course, they do differ in height as well, but primarily I think the effect of latitude. And there's some comparison figures for Elysium Mons and Olympus Mons. So this is one of the reasons we do our observations, to get these sorts of quantitative information. Let's have a look at some pretty pictures now. So this is going back to the 2010 opposition, by which I'm going to compare 2025. And we can see some pictures showing what they actually look like in the telescope. It's a really beautiful sight to see these. They look like little tufts of cotton wool on the disk of the planet, and very interesting to see. Another effect that you can see on the second slide is something that's almost absent from the old telescopic literature. And you can probably see on the right-hand side of each of those slides, you can probably see 3 dark dots. Yes, I don't know whether I've got anything I can point with. That might possibly be a pointer, but I don't know how it's turned on. So I'm probably going to not direct it in somebody's eyes. But if I go over here and I point, can you see those 3? Well, if you can't, you need your eyesight tested anyway. So. And those are the Tharsis Montes, okay? And you can see them on each of the slides. And the reason we see them there, we can see them, they're actually surrounded by lower cloud, and their summits are poking through the cloud. And that's a really lovely spectacle. And I often wondered why the earlier observers never drew that. And maybe it was something that they saw, but they thought shouldn't be there. Because it's something that doesn't occur on the afternoon side. You don't see the dark spots in the afternoon. Perhaps it was something that was conveniently ignored. And I go back through many thousands of drawings, and I can't find any really historic observations of these dark spots occurring on the morning side of the disk. And that's interesting. That says something about the psychology of observers, I'm sure. Okay, well, one of the most spectacular things we can see is what's called the AMEC, or the Arsia Mons elongated cloud. And I said that Arsia Mons was slightly different to the others. And one of the most remarkable images returned by, this is Viking, this is 1976, this picture. And you can see the 3 Tharsis Montes, and this whopping great banner cloud. That's something of a banner cloud. It's going halfway around the planet almost, or that part that's visible. So it's a most spectacular object, really spectacular. It's quite difficult to see this in the telescopic observations. You just have to catch it at precisely the right season. And here's another little puzzle that was extremely puzzling to me in 1988, when I was also effectively the director of the Mars section. And on the morning side of the disk, there was a little dark spot. Now, we assumed at the time that this could only be a shadow, because it couldn't really be anything else. And yet, the phase was full, so how could it be a shadow? It couldn't be the shadow of a volcano, because the volcano wouldn't be high enough to cast a shadow like that. And the observations were repeated in 2003 at the same season there. We can see a nice image in the middle there by Ed Grafton, for example, and one on the left by Isao Miyazaki. And there the matter rested. We didn't know really what it was the shadow of, but it all became clear in the recent opposition. So we're going to 2020 now, and I've got a nice image on the upper left there, and I've arrowed this mysterious dark spot again. And we've got a map projection, which has been made by an observer in Japan, and Arsia Mons is a slightly brighter area at longitude 120. And the streak to the right of it that's following it is not the shadow of the mountain, it's the shadow of the cloud. And that's really very interesting to see. And some of you will remember the excellent images that the late Peter Edwards took, a really marvellous planetary imager who tragically died a couple of years ago. And he can, if you have a look at that picture there from October 2020, we've actually got a little dark streak there on that image, which is again the shadow of the cloud. And on the right-hand side, a really high-resolution image by Damien Peach showing this really small shadow and the bright, slightly brighter cloud to the south of that. So it's a very interesting thing to see, but all the conditions have got to be right. The illumination has got to be right, the season has got to be right, the tilt has got to be right, because if the cloud lies above its own shadow, you're not going to see it. So on this occasion, the value of the latitude of the solar centre of this seen from the Earth and the Sun differed slightly, just enough for us to be able to see that. Okay, a little bit about dust storms. I'm not going to say so much about that. The first drawing here, you can see the markings appear unbelievably faint, and that is because we had a regional dust storm occurring. Regional dust storms are defined as storms whose long axis is 2,000 kilometres in length or more, but not encircling the planet. Anything smaller than 2,000 kilometres is called a local storm. And if we go down to the fourth row, the middle two drawings there also show faintness of the markings due to another dust storm that's occurred. I've mentioned the range of perihelic and aphelic oppositions, and I've said that what the seasonal dates are. Now, if we want to see dust storms around the North Polar Cap, we need to look in northern spring and northern summer. We want to see them around the South Polar Cap, southern spring and southern summer. If we want to see a very large dust storm, we need to look in the southern hemisphere summer from LS 180 on. Now, any of you who are thinking of trying to do that this year, you've already missed the chance almost, because Mars has been observable for some time, but you can also always see smaller dust storms which might occur from time to time, especially around the edge of the polar cap. And again, like the white clouds, the dust storms aren't precisely repeatable every season. I've got a comparison here. The line underneath each year, the coloured line there, underneath 1909, 2001, 2003, shows the range over which observations were made. The red rectangles show global dust storms, and the yellow boxes show regional storms. So you can see there was a global dust storm, planet encircling storm, 1909, 2001, but not in 2003. Instead, we had a number of regional events instead. So that's very interesting. And another thing that modern observations can do is to explain and interpret earlier drawings. So 1931, director of the Jupiter section was T.E.R. Phillips, and he also observed Mars, and on that drawing there he's got a little bright spot near the North Polar Cap, which was a dust storm over the Utopia region, and these images here by various people show a similar event in 2009. So these events are very interesting. They repeat from time to time, and they enable us to interpret historical observations rather well. We can also see, as I mentioned earlier, that on that October 1996 image by the HST of the North Polar Cap, we've got a band of dust over that cap. So that's all very interesting to see and to report and to try and get the statistics for that. So in 2010, we had dust storms the edge of the cap and also over part of the cap. I'm only going to show one example there, and it's perhaps best shown on the middle two images where we've got some orange dust outside the cap and a dark, what appears to be a rift in the cap, but it's actually dust crossing the polar cap. And as I say, this is very interesting to see at the time. And here we have, again, some images. At the top, we've got the bottom half of the image, and below that, we've done a polar projection to show how the dust is moving across the polar cap. And I think it's particularly well shown on this one here. You see that massive belt of orange dust crossing the polar cap. And of course, this will have some effect on the recession of the cap. Well, let's go on quickly. There are lovely maps available at the Mars section website. Here's a wonderful example by Martin Lewis, who always seems to get an enormous amount of detail. He's got an enormous amount of writing on this slide as well, which I won't trouble you with. I'll say it's online at the website if you want to see it. And there it is without the writing. And it's very interesting to see how these albedo features change from year to year. And we know now that a feature will fade if dust is deposited on it, and it may darken if dust is removed from a certain locality, exposing the underlying bedrock. If you remove dust from the Hallis Basin, we don't tend to see an albedo change because the dust is so deep. So this gives us all sorts of interesting information. And as it says here, maps of the planet and the standard albedo maps can be found at the Mars section website. And I just put a brighter slide there in case anyone has fallen asleep at this point. And I'm going to give just one example. There was a very, very dark marking called Nepenthes, which linked Utopia to the side of Syrtis Major for many, many years, up until the decade of the 1960s. And during that time, there were frequent dust storms over the region called Isidis Regio, or Isidis Planum, and these dust storms tended to keep this marking dark by excavating dust constantly from that area. And for some reason, these stopped after 1963. We don't see them again in the telescopic record, hardly at all, and this marking has returned to its desert appearance, as we can see here. Two drawings on the left by Antoniadi using the 33-inch refractor at Murdon. The one on the left, 1909, the feature isn't there. 1911, a dark feature 2,000 miles long has suddenly appeared. 1988, a drawing by me with the same telescope, shows that that marking has disappeared. So two conclusions can be drawn from this slide. One, that this marking has disappeared, and secondly, that Antoniadi was much better at drawing small dots than I am. Okay, we've mentioned this slide already. Another feature that's very changeable at the moment is a feature between Mare Acidalium, which is the main marking in the northern hemisphere, and Oxyopalus and Margaret of Asinus. And as you can see on these three drawings by myself, 1988, 2003, 2020, we can see a dark channel has formed between Oxyopalus there and Mare Acidalium, which is called on the old telescopic maps Indus, and it looks just like a canal, just as Percival Lowell might have drawn it a century ago. So some of these things that are on the old telescopic maps were not imaginary, they were real features caused by dust storm activity. Okay, so I'm going to skip over that as time is going, and I'm just going to show you. Now, Martin, if you're watching this anywhere, I'm sorry, I'm going to deface your beautiful maps. And I just thought the other day how nice it would be to get a spray can and spray over this map with the bits that have gone darker and the bits that have gone brighter over the last 100 years. So here we go. So I've horribly defaced his map, and I do apologise. I'm not going to publish this, don't worry. So we can see here that the great curve of Nepenthes on the left of Syrtis Major has disappeared, and we can see many other variations which represent long-term changes. Coupled with this, there are often changeable regions. For example, this one here, just above the equator at longitude 360, this is the Pandori Fretum, and it used to be thought this was a seasonal change due to the release of water along the Martian canals from the polar cap. And we now know it's due to the direction of dust storms leaving the Hallis Basin and travelling to the west out of that basin and picking up dust and darkening the underlying terrain. And so there are a lot of regular changes which are a result of dust storms, but aren't sort of, if you like, progressive changes over the years. A few predictions for 2024 to 25. Well, the apparition has already begun. Solar conjunction was as long ago as last November. We've already had the spring equinox in the southern hemisphere, which is the beginning of the dust storm season, and you'll be able to read all of these dates in the June issue of the journal or online. So what we're going to do, we're going to be checking for dust storm activity at the edge of the caps and all of those regular phenomena that I've talked about. I've chosen these images from 2010 by Andrea Tassali of Lincoln with I think a 12-inch reflector to show some of the typical things that you might see in January, February and March next year. So this is the sort of thing you'll be able to see, and these two will appear in the June journal. I'm going to end with some early observations, and some early observations. Most of the observations done so far have been done by our member Clyde Foster. By the way, he sent me an email this morning saying, say hello to the meeting. So I'm saying hello from Clyde in Namibia. And he took some marvellous images when the planet was only 3 arc seconds inside. And I'm going to finish by going through them quickly. Now, I should say on the right is a WIN-JUPOS simulation. And that disappears. And we've got red images, we've got infrared, we've got blue, we've got green, and we've got the colour composite. And you can see, as I go through them, the albedo markings clearly seen, and so far no evidence of dust so far. And I'll go through these just to show you them quickly, and it won't take more than a few moments to show you these marvellous images that he's got, with the planet now having increased to an enormous 4 arcseconds of size. 14 it will be next January, but don't miss it because it'll soon shrink from that magic figure. And I think we end with, there's one here which even shows the fast, this one here, if you look at the original image, probably not on this screen here, but you can see the original, the individual Tharsis Montes. That's how good the images are. And this is the last one which he took this morning. And just before I got on the train, I took out the memory stick one last time to change it and put on this image from this morning. So Mars is being observed. If you can get up in the early morning and make an observation from Britain, you'll be doing a grand service to the association in the usual tradition of its observational programme. And I will close on that note and say, don't forget to send in your observations to the BAA in 2024 and 25. Read the blog that's about to start on the Mars section website. And above all, good luck. Thank you.
Thank you very much, Richard. I hope that's inspired you all to get out in the early morning and start getting practice at observing Mars. Got time for one or two quick questions, if there are any. Jeremy.
A couple of questions about the polar caps. So in the North Polar Cap, you show the sun, the dunes rather, nearby. Are they constraining the cap in some way? Or is there an interaction in some way, or is it coincidental?
I don't know the answer to that. I suspect their position is partly due to the fact that we have circumpolar winds around the cap, which are probably to do a lot with it, and also the rift formation in the cap. So I've seen papers published which suggest that it's the pattern of winds over the cap over geological time that have caused these patterns to occur. So it might be the same with the dune field, but I don't know because it's not really my field, unfortunately.
So, and the southern polar cap, you said, recedes asymmetrically?
It does, yes.
What reason why?
Yes, I mean, there are partial height differences, but again, I've seen some papers which suggest that the air currents near the South Pole have been altered by the presence of that giant impact basin, Hellas. And we don't have such a feature in the northern hemisphere. We've got it in the south, and there's some papers being published which suggest that that is changing somehow the wind structure near the pole, which is causing that asymmetry in the ice distribution. But unfortunately, I can't give you a better answer.
Thank you.
Okay, Nick.
Just a quick question. You mentioned about the Tharsis volcanoes not being in historical visual observations, but being prominent in images now. Are they actually prominent visually? So just trying to understand, is it that you see them visually because you know that they're there?
Yes. I should explain that the clouds over them have always been seen. Those records of the clouds go back to the 19th century. Seeing them as dark spots, that's been done, but seeing them as dark spots surrounded by the white cloud, that is something that doesn't seem to appear until the 1990s, really. I go back to the earlier drawings, and I just wonder, it might have been a lack of resolution, because, and of course, the CCD images that showed them for the first time were, of course, highly processed. But you can see them visually, but they are, even with the 16-inch reflector, I find quite difficult to see all three. It's really at the limit of what you can do visually. And that shows the extent to which the observer has been helped by the digital era. So it might just have not been quite enough contrast, but I do find it strange. It might have been that the observer saw it and thought it shouldn't have been there.
No, I don't recall seeing those.
There's still time.
Right. Well, thank you very much, Richard, for an excellent rundown. And more to Mars than you might at first think. Well, we're going to move outwards in the solar system now to the giant planet Jupiter and its giant system. And John Rogers is our expert to talk about Jupiter and Io in 2023 to 2024. So, the floor is yours, John.
Well, thank you, Mr. President. Yes, there's a lot to say, and I'm going to be talking partly about the amateur observations that the Jupiter section is constantly receiving, and partly about Juno's observations from orbit. Can we get the talk up? So the first half will be about the observations that we have as amateurs, because the amateur imaging has reached a tremendous level of expertise nowadays. Okay, thank you. Here's a recent map made by Rob Bullen from various observers' images. I'm not going to talk about all of those arrowed features on it, but you can just see the general pattern of the belts and zones, and mostly is pretty much normal at the moment. The one anomaly really is that the North Temperate Belt, which is normally here, is currently absent, and I'll explain how that fits into cycles of Jupiter's meteorological activity as the talk goes on. The North Equatorial Belt has also got quite a lot of activity in it, which looks fairly normal, but may lead on to other things. The equatorial, oops, that was not too sensitive. Equatorial zone is now clear of colour. The Great Red Spot, which is, I think I'm not going to use the cursor because it's a bit sensitive for me, is down and towards lower right. It's now the somewhat little red spot. It seems to be progressively shrinking and is now as small as it's ever been. But I said Io because there's quite a few amateur images showing the Jovian satellites, including Io at great high resolution. But also the Juno orbiter has not only been taking great images of Jupiter, which I'll show you a few, also very recently it had 2 flybys of Io, very close, the first close flybys for more than 20 years, producing several really spectacular images. But first, let's wind back 50 years. Curiously, this slide is very much a counterpart to one that Richard just showed. An image from 1973. We just realized in December it was the 50th anniversary of the first spacecraft flyby of Io. And here is an image taken by Pioneer 10 as it closed in, contrasted with an image by Damien Peach 50 years later. And so you can see a lot more detail in that image by Damien. And incidentally, on both images you can see the shadow of Io on the planet and Io itself on Damien's image. To give Pioneer its due, here up in the top right, oops, is Pioneer 10's best image. The resolution is a bit better, but it's still somewhat inferior to these 2 images taken by British observers, BAA members, Martin Lewis and Peter Tickner, last autumn. And in fact, one of the great things in this last apparition has been that Jupiter is at a good high declination. As you all know, it's been high in the sky. And so some British observers managed to get really good images. And indeed, all across the Northern Hemisphere, particularly Southern Europe, they've been getting images which, until recently, in previous apparitions, we were only getting from the tropics and from Australia. Here's a couple more images, one from Damien, one from Martin Lewis, showing Io in transit at close to the time of opposition. And in the lower part of it, you can see enlargements of Io, where you can see quite a lot of features on the little moon. And the bottom row represents WinJupos simulations showing spacecraft data. So the polar caps of Io, it has dark polar caps, which you can clearly see in all these images. They used to be something that was an amazing achievement, anyone to record at all, visually or by photography. Nowadays, they're routinely recorded in people's webcam images, and you can even see some features in the equatorial zone there, which represent real features, though they're never clearly resolved in ground-based images. Also, at lower right there, you see one of Martin's images of Ganymede. You can see the original image of it at top right there, in the same one as the Io transit. On that image, you can see some real dark features and a bright spot which represents a ray crater. Here are some more images from lower latitudes, mostly in the tropics, showing images of Io and Ganymede in transit last November, within a few days of opposition. And the great thing at that time is that you can see the satellite projected in front of its shadow. So there's a couple of beautiful events there. And again, you can see surface details on the moons themselves, which can be matched up with the spacecraft data shown in the WinJupos simulations. But again, going back to a British observer, Tom Williams in Wiltshire, has been piecing together some of his images of Ganymede over the last 2 years. And this is quite an achievement because not only is the resolution great, but he's managed to get rid of the edge fringing, which is normally a contrast of the contrast effect when the satellite is off Jupiter's disk. And so from these 5 images, and I think one more, he's produced this global map of Jupiter seen there in the middle. And you can see, comparing with the spacecraft map down below, a NASA map, you can see quite a lot of the dark areas are shown faithfully in his map, and at least 2, probably more, of the bright ray craters are also represented. But incidentally, Ganymede also has polar caps, although these maps don't quite go up to the poles, I think. On the spacecraft map at the bottom, you can see there are white bands top and bottom, which represent water frost that is deposited in the polar regions. And you can see the same up, at least in the northern, upper fringe of Tom's map there. So turning to the planet itself, when we look at the highest resolution images, here's a pair by Christopher Goh in the Philippines and Eric Sussenbach in Curaçao in the Caribbean. This is a pair of images taken on June 27th, almost exactly 10 hours apart. That is one rotation of the planet. And in fact, while British observers were having great trouble seeing anything because of the appalling rainy weather that developed from November onwards, observers at some lower latitudes were still able to take superb images. And Eric and Chris managed to get images some 10 hours apart on quite a lot of dates during December. So images of this quality not only show us fantastic detail in all sorts of regions we might be interested in, but they also enable us to measure the wind speeds around the planet. In this blink, you can see the jet streams in many latitudes of the planet. The whole of the equator is blowing to the east, that is to the right. So when this blinks with the equator to the right, that's forward, and then it goes back again. But if you look up towards the polar regions, you can see movements towards the east or towards the west in alternating patterns up there as well. I think you can also, perhaps on the screen, see some movement in the Great Red Spot, which is rotating. And these images enable one to actually measure the wind speeds, not merely of individual points, but of the patterns of clouds as a whole over the planet. And this was done by Grisha Hahn of the Jupros team, using 4 pairs of images like the one I just showed you. So this is his zonal wind profile from those images from December, January 2023, 24. And it shows us the jet streams in all the regions of the planet. And mostly it looks very similar to well-known spacecraft zonal wind profiles for Jupiter. But some of these more rapid jet streams have interesting variations that correlate with cyclic changes in the meteorology of the planet that can lead to really spectacular events that we can all observe with our telescopes. And in particular, I'd like to show the one down at the bottom there labeled North Temperate Belt South Edge. That one was a bit faster than in most of the spacecraft data in Grisha's zonal wind profile that you see here. And that tells us that we can expect another spectacular outbreak sometime in the next 2 years. So this is a chart of the wind speeds measured for that jet stream. It's the fastest jet stream on the planet. It defines the south edge of the North Temperate Belt, and its speed varies considerably with this cycle of about 5 years, more recently 4 years. At least sometimes it does. Since 2007 it's been doing that. In earlier eras, historically, it has done that, but then also it has static periods, which you see to the left here of this diagram. In the 1990s, the wind speed was constant and not as fast as at many other times. And the wind speed seems to gradually accelerate until you get a brilliant outbreak of white spots on the south edge of the belt. The belt at that time is normally very faint or absent, as it is now, and the white spots then produce a spectacular outbreak that spreads around the planet and reconstitutes the belt with immense turbulence. And you can see how the wind speed appears to ramp up somewhat irregularly, but generally towards a critical speed. And once it exceeds that speed, you can have one of these enormous outbreaks. Well, the wind speed that Grisha just measured is the most right-hand point on this chart, the dark blue one, And it shows that the speed is indeed accelerating up towards that critical level. So given the periodicity of 4 to 5 years, we can expect another great outbreak in 2024 or 2025. This is what one looks like. It's up there directly above the Great Red Spot. There's this brilliant white spot in the North Tropical Zone, North Temperate Belt South Edge, with a trail of turbulence behind it that will grow bigger as it rushes around the planet at high speed and gradually reconstitutes the North Temperate Belt. We might even expect something more than just an outbreak on that belt, because this is a series of excerpts from maps of the planet showing the last 3 such events. In 2012 on the left, and 2017 in the middle, 2020 on the right. Within the few months after the white spot outbreak that you can see there on the right, the belt reconstitutes, and initially it's a vivid red colour. So that's what you see in 2012 and 2017. It wasn't quite so vivid in 2020, though there was definitely some colour there. But this also coincided in each of these 3 years with a massive broadening of the North Equatorial Belt to the north. So you can see there in 2011, look on the left, 2012 there, you have this immense orange turbulent pattern from nearly the equator up to the north edge of the North Temperate Belt. So we nicknamed that a Great Northern Upheaval. And we see a similar pattern in 2017 and a similar pattern in late 2020. Now, these NEB expansion events also are cyclic and normally have a period of between 3 and 5 years, but because of irregularities in the periods of both events on both belts, they've managed to almost coincide in these last 3 events. So is that a real phenomenon, or is it just coincidence? Is it going to happen again in 2024 or 2025? Well, that's something we have to just observe and find out, but it's certainly a remarkable thing to see. What has the NEB actually been doing during this period? Well, starting again in 2020 there on the left, with the NEB becoming very broad, it then narrowed drastically in 2021. In fact, more narrow, the northern 2/3 of it being very faint, more narrow than ever before in the last century. So we expected something really spectacular would happen to broaden it. But that didn't actually happen. What happened was really tiny little outbreaks, these tiny white spots you can see in some of those panels. I think the 2nd and 4th panel you can see some. Tiny white spots within the residual very dark brown belt. And they were little convective outbreaks, that is thunderstorms in fact, which disturbed the belt, disrupted the white cloud cover, spread the dark coloration a little bit further. They were quite small and transient. Gradually, over a year or more, they pushed the north edge of the belt back to where it normally is. But in the last 6 months or so, it seems that it may be going beyond that. There have been bigger rift outbreaks. Rift by rift, I mean one of these bright white spot outbreaks, but generating an oblique white streak through the belt. And going a bit further north and getting to the stage where we think we might be getting into a new NEB expansion event already. This is a series of images, just excerpts from a long, dense series that amateurs all around the world have been able to produce, showing the onset of a particularly bright and long-lived energetic rift, starting with a new plume, a white spot, convecting up in the middle of the belt, and it evolved over a matter of days. But these are at almost one-day intervals in October, and then a bit of a gap, and then some more of them. You can see it stretching out into an oblique shape, extending tendrils of bright white clouds to north and south, and in some cases twisting around that region that is marked on the right as a faded barge. That's a cyclonic circulation, a particularly large one in the belt. Unusually, it doesn't have much contrast, but it's certainly a well-marked cyclonic circulation. And in some of these images, you can see the white clouds from this outbreak being twisted around it by the winds that circulate around it. So the rifting from this is still going on, and we wait to see how it develops. But in the meantime, Juno, taking images every, I think it was 43 days at the time, managed to catch some really nice images of this feature. Juno doesn't catch images of the whole planet on every, doesn't catch close-ups of the whole planet on every orbit, but on this occasion it did, October 15th, just a week after that initial outbreak. And here you can see a JunoCam close-up showing many interesting circulations that we've been tracking for some time in that region, including that faded barge circulation and that bright plume within the NEB that had just erupted close by. Fortunately, Juno also managed to image the same thing on the next two orbits. So this was the third such event, Perigeo 57, that's its 57th orbit, on December 30th. And there you see a lot of beautiful new detail as well, including a series of waves running across that faded barge that we hadn't seen before. And another of the little plumes. This is not the big one, this is one of these little eruptions that happened in the south part of the belt. But you can also see one other thing marked on this image, impact flash, 12 hours earlier, up there at top right. So what's all that about? Well, amateurs nowadays, when reviewing their videos of the planet, as they produce images from their webcams, occasionally observe a bright flash on the planet. There have now been 13 of these since 2010, and in fact 4 of them were observed in 2023, which is the greatest number observed in any year. And these are impact flashes, i.e. fireballs in the atmosphere of Jupiter, where a little asteroid or comet, probably several meters to 10 meters in diameter, smashes into the atmosphere of Jupiter and burns up and explodes. So this is an observation of one of those impact flashes in 2023, November, by a Japanese observer. This is typical of what it actually recorded. The actual video showing what the seeing is like at the time and showing the flash itself has a speckle phenomenon because the seeing is not at all good. But from those it's possible to extract the position, do an integrated image of the flash, and superimpose it on a more extensively integrated image of the planet itself. So you see that on the left hand here, the flash of August 28th by other Japanese observers. Then in the middle, you have one that was reported on December the 28th. Now that one was actually seen by an observer in Puerto Rico, Efrain Morales Rivera, who is a very experienced imager, but at the time, he didn't happen to be recording. He saw a flash on his screen. He noted exactly where it was, he reported it immediately, and then an imager in Brazil, Conrado Serodio, who happened to be recording an image at the time, searched through his video and found just one frame that showed this rather faint flash that's arrowed there. We think that's probably real, because both are experienced observers. That single frame that Conrado recorded is in the location that Efrain said his was seen, and it was probably a real but comparatively faint flash. Mostly they're recorded over 1 to 2 seconds, and so are recorded in plenty of frames on the video. That was the case with the fourth of these flashes last year on December 29th, exactly 24 hours and 4 minutes after the previous flash, remarkably. But not evidently anything to do with the previous flash. Anyway, you see it there up in the northern hemisphere, and it was quite a bright one. And that one happened to be just 12 hours before JunoCam took this image. Now, in the circle which marks where the flash was, there is nothing to see that's out of the ordinary. We're not surprised at that, because with the previous 12 flashes that have been seen since 2010, there has never been any relic of the flash, no black spots like in the much larger impacts left by the SL9 impacts in 1994. But this is the soonest after an impact that any spacecraft has managed to image it. So the negative result there is a very significant observation. So well done to Andres Arboleda for recording the thing, and great fortune that JunoCam was imaging just 12 hours later. So what about the Juno mission? Well, Juno is still in orbit, as you may well know. It's going to remain in orbit until September 2025, and it's mostly still working well. The radiation and the length of time it's been up there are beginning to take their toll. We've had a few missed images or missed whole perisodes of imaging, but basically the JunoCam team have managed to fix that, and it's still working very well at the moment. Now, as the mission has evolved, the orbit has also evolved. So it's not really imaging in the same way that it was early in the mission. Now, this is a side view of Juno's orbit around Jupiter. If I can put this thing, no, I can't. This, trying to move the cursor, no. The orbit began as a polar orbit, and the line between perigove and apogee, I think that's called the line of apsides or the line of apsides, that was in the equatorial plane. But as the mission has gone on, due to, I suppose, weak planetary perturbations, the orbit has gradually shifted round. So the perigove is now in the northern hemisphere. And so if you look at all these parallel lines in the upper part of the image, they're gradually getting lower as these represent the inbound trajectory on each orbit. And as that's happened, the inbound trajectory has come to the stage where it is crossing the planes of the orbits of the satellites. So at perigove 34, on the left, it crossed the orbit of Ganymede, and it was arranged so that it did a very close flyby of Ganymede at that time, and it took splendid images. Perigove 45, a year or so later, it did the same with Europa and crossed the orbit of Europa. And ever since then, on every alternate orbit, it was arranged that it would get closer and closer to Io, until perigove 57 and 58, just last winter, it did very close flybys of Io. Of course, we didn't know whether those images would be successful. The camera was never designed to image satellites traveling at hugely high speed past them at close quarters. But it has indeed worked tremendously well. Another aspect of the changing orbit has been that Juno sees the lighting conditions on the planet very differently. At perigove 1, when it first started, it was doing a flyby over the evening terminator, and then as Jupiter moved around the Sun, while the orbit stayed in approximately the same plane, Juno's perigove moved closer and closer to midday, so it was getting close-ups of everything beautifully illuminated. Then it moved round to the morning terminator, but since perigove 50, the perigove itself, the closest approach, has been on the dark side. However, that means that the approach is on the bright side. So we now get a superb series of images as Juno moves in towards its closest approach. So here, I'll show you just a few of them from those last two perigoves, or the approach thereto. You start off with rather distant images, but still pretty good, showing, as you move in over the southern hemisphere, these are a couple showing the Great Red Spot and showing a shadow transit of Io passing over it. Juno gets closer, the resolution gets better and better until you see really nice images of the North Equatorial Belt, like those that I showed you recently. And during that process, Jupiter undergoes at least one rotation. Sometimes if Juno can start imaging far out and isn't distracted by Io, it will cover two rotations. And so Gerald Ashtet, who processes and makes maps of all these images, can make planet-wide maps. This is one of them from perigove 57, and all the features arrowed there are features that we have been tracking for a long time from the Earth, and we're very interested to see how they're evolving and what Juno can show of them. Juno then comes in low over the North Polar region, one of its close-ups here showing some of these high latitude features, and then passes nicely low, about 10,000 kilometers or so on altitude nowadays, over the North Polar region itself. And so it has these beautiful close-ups of the North Polar cyclones. Here you see one of them, a most spectacular feature. That's some 4,000 to 5,000 kilometers across, this area of the bright white clouds with darker red clouds in between. Those very bright clouds on the edge of this feature are thunderstorms, as far as we can tell. Down to lower right, there's another cyclone with much darker appearance because the clouds are thinner there. There are actually 8 of these circumpolar cyclones in an octagon around another cyclone at the North Pole. And you see them here when we put together North Polar maps from the 2 successive perijoves, because we never see the whole lot at one perijove because of the lighting conditions and how fast the flyby is. So these 8 cyclones around the central one have been there ever since the mission started. That's nearly 7 years ago now. It's a similar map from the previous pair of cyclones, previous pair of orbits about a year earlier. The features around those circumpolar cyclones have changed tremendously. They changed massively even between 2 orbits. But the 8 cyclones have remained there. They have more or less retained their original appearance. So they're an island of stability, what physicists call a vortex crystal, in the midst of fantastically swirling, complex, chaotic and changeable features all around them. Here you can see their rotation at just one perijove. This is PJ58. On the right there, it's a pair of images over 26 minutes, and you can see the rotation of these 3 circumpolar cyclones there. There's also a smaller cyclone on the left, and the bright white spot down to lower left is an anticyclonic white oval. But you can see the rotation in those 3 cyclones nicely. And the pair on the left is a pair just 9 minutes apart, in which obviously the interval is much less, but you can just see that the interior of the topmost cyclone is rotating in the opposite direction. It's rotating like an anticyclone. There's a feature looking like an eye in the middle. And this is a fixed feature of these large cloud-filled circumpolar cyclones there, which I don't think the atmospheric physicists yet understand. It's an interesting one to be worked out. So after passing over the North Pole, Juno then passes over the terminator. JunoCam has been getting some close-up images of the cloud bands there, but all of this region is in haze. And we were hoping we'd see interesting details in these cloud bands, but I think all we're seeing is diffuse cloud bands at shorter range with beautiful colors and good material for photometry by the JunoCam team, I think. But what about Io? So this is an image of Io at perijove 55, but 2 orbits later, it was going to be viewed at much closer range. And here was the first and closest of the images at PJ 57 over the North Polar region. So on the left is sort of the image just normally processed. On the right, it is with the dark side brightened, because one of the great features of these flybys was that the dark side of Io was well illuminated by Jupiter. And Jupiter shine is about 5 times brighter than Earth shine on our moon, I believe. So it was possible to amplify the contrast in these images and show beautiful detail there. The North Pole is indicated by that white circle on the top right part of the image. And much of the area around the North Pole had never been mapped before. In the center of this image, you can see, for instance, a trio of mountains surrounded by white halos. Those were known as nothing more than white blobs on the Voyager images and the Galileo images. But now you see them as well-defined mountains, and so the same for many other features around. So these images map the North Polar region of Io for the first time, and just enlarging a part of the image which shows that trio of images, that trio of mountains there on the left. They're very like other mountains known on Io, but these are particularly good images. As you see, some of the mountains have really quite steep slopes and very sharp ridges and crevasses in them. On the other hand, they seem to be very fragile because there are huge aprons of debris that have evidently flowed down from the mountains across the surrounding plains. The one up the top, similar, seems to be a very sharply defined mountain with a huge debris flow. On the right of this enlargement, down to lower right, you can see 2 calderas. All the features that I've put arrows by on the right-hand image are volcanic calderas, which we know to be active. I'll show you that in a moment. At least they have warm, glowing lava, warm lava in them, and close-ups of them there. Shifting up a bit to see the more upper part of the image, the mountain up at top left here is very close to the North Pole, so we can use that as a fiducial mark for the North Pole. And at top center, you see a mountain there that falls directly down into a volcanic caldera. It's the one that's labeled Viva Svant, though I think it was nothing more than a small dark spot in earlier images. And that's actually also something that's seen often on Io, that the mountains often have a caldera right there at their base. We don't understand what that relationship is due to, but it seems to be a feature of the tectonics on Io. I said that all those arrowed features are volcanic calderas that are active, and we know that because another instrument on Juno, the GIRAM, the Juno Infrared Auroral Mapper, takes images at 5 microns in the infrared, where it can see the glowing heat of any warm lava that there might be on the surface. And it routinely images around 100 hotspots over the surface of Io, which are either volcanic calderas, most of them here, or active lava flows. In fact, there's one of those up near the top here. Yes. Sort of down there, labeled Tonetua. That's a volcanic lava flow that developed during the Juno mission. Juno and GIRAM detected a plume over it from very long range earlier in the mission, and it's now become about a 200-kilometer long lava flow. So you can see that all these calderas are actually glowing, and there are other glowing features as well. However, at that first perigeo, perigeo 57, JunoCam did not record any volcanic plumes. What it did get was a close-up of the largest caldera of all, called Loki. That's the big dark spot at lower right there in this image, and labeled L in the GIRAM image on the left. So at the next perigeo, Juno got even nicer images of Loki. Still didn't record any plume, but what it did record was an extraordinary brightening of the surface as the solar illumination angle changed. The left-hand image is a direct image. The central one was a narrower crescent image, but here it has been reprojected as if from the same viewpoint. That's the left-hand image. And what you see, and what is animated on the right-hand side here, is the brightening of the surface of the Loki caldera. This is a sheet of lava, 200 kilometers across, solidified lava, of course. You don't get liquid lava that remains exposed to the space like that. But this is presumably basalt, and it would have a glassy surface, which is reflecting the sunlight as the solar angle changes. And the yellow arrows in the left images indicate other calderas, much smaller calderas, where the same effect is seen. One of them, labeled Mazda North, is particularly bright there. So there, yes. That one shows particularly bright reflectance. In the others, the reflectance is either dimmer or consists of a very small spot, which you might not be able to see on the screen here. But the effect in Loki is really striking. We can also say, have there been changes in Loki recently? We're comparing here with the maps from Voyager, from Galileo, and from Juno. Well, what we can say is there have actually not been major changes around it. Most of the apparent differences between these maps are due to changes in lighting conditions and perhaps in the filters used by the different spacecraft as well, because the appearance of areas on Io is very sensitive to the lighting angle, the viewing angle, and the filters used. So during the Voyager mission, there was a big active plume erupting from Loki. In fact, from the dark stripes that are just up there, just upper right from the big caldera. And there seems to have been an active lava flow at the time outside the caldera. And you can see that the shape of those dark stripes, which are the lava flows, had changed by the time the Galileo orbiter was imaging it in the late 1990s. But between Galileo and Juno, there does not seem to have been any definite change in those patterns. So we know from Galileo that there were lava flows spreading across the surface of the caldera. So it was all rather like the Hawaiian volcano, Halemaumau, is at the moment. The caldera has got a lava lake in it, which is covered in solid, dark, shiny basalt, and lava from time to time erupts from one part or other of that caldera and spreads another lava flow over the top. That was happening during the Galileo mission in Loki on a probably 100 times greater scale than in Hawaii, and it may well still be carrying on because Loki is always an intense hotspot. But there doesn't seem to have been any activity outside the caldera. However, when it came to PJ58, JunoCam did record some active plumes, and here are the 3 images that recorded it. And incidentally, the left-hand 2 images, there is no sunlight at all. All the illumination there is from Jupiter shine, with the images having been beautifully enhanced and the dark sky enhanced even more to show the plumes. So in the left-hand one there, you see a plume over a volcanic complex called Masubi, which was erupting in the Voyager days and has been recorded intermittently since then. There may even be continuous eruptions from Masubi. In the center, you see that same region from the opposite side. It rather looks as if there is a plume near Masubi, but it's not over Masubi. We think that it's over a volcano called Kanehikili, which is up here at top left. In fact, that has never been imaged at such high resolution as it is in this picture from Juno. You can see here it clearly consists of 2 different volcanic centers with rather complex lava flows and volcanic deposits around them. So it seems that the plume shown there on the limb is over one of those volcanic centers. And then at bottom right there's a 3rd plume visible, which is over some unnamed volcano, which is not recorded in the Voyager maps, down towards the South Pole. So Io's volcanic activity is still continuing. So I'll leave off the Juno section with this complete version of one of those beautiful pictures of the dark side of Io, illuminated by Jupiter, showing this fantastic panorama of nothing but volcanoes all over the surface. But I want to just show a couple more slides about Io, getting back to British amateur observations. Chris Hooker, whose work you may have seen on the website, I think Nick showed one of his images at the previous meeting. Chris Hooker has been taking images of Io in sodium light, using a filter for the sodium D lines, in order to try and record the sodium clouds and jets that professional astronomers have long observed around Io. And this consists of sodium atoms, which, along with the sulfur and oxygen atoms that surround Jupiter in its magnetosphere, ultimately come from Io's volcanoes. They're not ejected directly from the volcanoes. They're apparently scoured from the atmosphere and perhaps from the surface by Jupiter's magnetic field, which contains a massive energetic plasma. And as that rushes round Io with Jupiter's rotation period, it scours these atoms from Io and converts them into rapid jets and a cloud that are being emitted from the satellite. So Chris Hooker has been able to record this jet the first time that any amateur has done it. And here he's taken a sequence of 5 images over 4 hours, showing how it changes. So I guess you can see Io is the most right-hand of the satellites here in this series, and the jet is extending out from it. And the angle of the jet changes tremendously over these 4 hours. That is actually understood because of previous professional observations. Because of its interaction with the magnetosphere, the angle of the jet depends on the angle of Jupiter's magnetic field and the position of Io's orbit. In this sequence, Io is moving gradually away from us at the right-hand answer of its orbit. And so it's going to be rather hard to tell whether there are any changes in this jet. One motivation for doing this was that professionals are doing a particular campaign to observe Io at the moment in conjunction with Juno's flybys, and it would be very useful to have amateur observations from a longitude that professionals are not observing from to see if there are any changes in this jet. But how are we going to know if there are any changes? Well, the easiest thing to do is simply to look at intervals of 1 week, or particularly 7 days and 1 hour. because in that period, there's exactly 4 orbits of Io, so it's in the same position in its orbit, and a more or less an exact number of rotations of Jupiter, so that its magnetic field is in more or less the same orientation as viewed from Earth. And Chris did manage to do that on 3 successive weeks in August, September last year. And you can see here, in this case, Io is the, is the one on the right closest to Jupiter. And you can see a jet or cloud pointing out in both directions from Io, one of them down to bottom right. Now, the fact that it extends much further down in the last image than in the earlier ones is really due to his improving technique. He was still developing his technique over this period. But it does show that, indeed, if you look at intervals a week apart, you do get essentially the same configuration of the cloud and the jet. So he'll be continuing this work in the next apparition. Well, this is some of his more recent observations where he's managed to increase the sensitivity even further. I guess that's probably it for this apparition. He's been much frustrated by the rains over the winter. But hopefully next apparition he'll be able to continue with this work with Jupiter high in the sky. Okay, that's the whole of the talk. Thank you for your attention. And if there is any time for any questions, I'm happy to. I know Nick has got some things to say.
Time for any questions? Any questions? Very good.
I just wondered, is it known why the great red spot is shrinking so much?
Not really. Atmospheric physicists are certainly looking into the balance of energy going into it and energy out of it. I should say that it's not difficult for the physicists to model a long-lived anticyclone in Jupiter's atmosphere. Because there's no friction on the planet, once you've got one there, it can keep going for a very long time. And one can see small vortices that merge with it from time to time. And these could be feeding energy into it. On the other hand, they could be draining energy out of it. And the physicists are not at all sure what they should be doing. Anyway, I think more theoretical work on this is needed, and perhaps integration with Juno's observations, which have shown that the Great Red Spot extends quite a long way deep, but not as deep as the rest of the jets on the planet. So that's more grist to the theoretician's mill.
Any other questions? Jeremy.
The iron tail, sodium iron tail, in the last series, they seem to be diametrically opposite.
The 2 jets, yes.
But not linearly.
No, it's a very complex situation. There is a cloud which always is present with Juno in its orbit. They're called the banana-shaped cloud. Then there are jets which are dragged out by the magnetosphere over a shorter time frame and change their orientation very radically according to the instantaneous orientation of the magnetic field. And then there's a stream that extends quite some way out from Io's orbit. And sometimes you're seeing the stream superimposed on Io with it being seen beyond or nearer than Io, and therefore seen on both sides of the moon. So it's a very complex situation, much more complex than we expected when we got into this.
Yes, John, fascinating talk. You mentioned earlier on is it the North Temperate Zone? There's a wind, you said was the quickest jet stream on Jupiter. It's always struck me that there's this asymmetry between the North and the South on Jupiter. Do we know why that's the fastest stream? And does it have a counterpart in the Southern Hemisphere?
I'm afraid we don't know why. Obviously, in the South, you have much more well-defined large anticyclonic ovals, the Great Red Spot being the flagship. So those are quite likely taking up energy that is not accommodated in the jets. In the North, for some reason, the anticyclonic ovals are mostly smaller, and there is more energy in that one tremendously powerful jet.
Right.
So perhaps 2 alternative solutions to the same dynamical problem. We don't really know.
Okay.
David Boyd.
I've also been able to record the sodium cloud spectroscopically.
Yes, you were. You published a little article in the journal about it.
Yeah.
Congratulations, yes. Would you be able to measure any changes in its brightness, you think? Preferably at intervals of 7 days and 1 hour.
Don't let try. The map you showed of Ganymede that was made by, I didn't catch his name.
Tom Williams.
Tom Williams, yes. Did you mention what size telescope he'd used to
Oh, I
capture
don't
images?
remember, I'm afraid. I don't think it was enormous,
Yeah.
but we'd have I could let you know.
Yeah,
or it is on
staggering
our
piece of work.
reports.
I think it might be a Celestron 14.
Really?
I think it's no bigger than a Celestron 14.
That's a C14, something of that sort. Yeah.
Thank you.
Well, that's, I think we're all stunned. Seeing things never seen before on Io.
Mountains on Io.
Right, well, thank you very much again. Finally, Nick James, Director of the Comet Section, is going to give us our regular rundown on recent observations and what to look forward to in the sky, which I think the solar eclipse will probably feature prominently, which is shortly off to lead an expedition in Mexico.
Sort of, yeah. Unfortunately, due to the fact we had a little hiccup with the streaming at the beginning of the meeting, I haven't put my talk on this laptop yet. So just bear with me a second. Hopefully it will see it.
How many people are going to the eclipse, incidentally?
I was going to ask that, but yeah.
The answer is about 6. Not
Would you mind
really,
just copying it?
It's not everybody. It's only a few lucky individuals.
Some people may have gone already.
Yes.
Thank you. But yeah, there's two main topics for the Sky Notes. Because Richard and John have already covered Mars and Jupiter, I'm not doing any Mars and Jupiter. So you might guess there might be quite a lot of comet stuff in this.
The more the merrier.
The more the merrier. It is a very nice comet. Grand. And is this... Right. Okay, so could we just have the lights down a little bit as well, please? Because these are faint, fuzzy things. Just wanted to start off. Mazen Yunus has been posting some fantastic pictures to the BAA gallery, and this is one of his. In fact, could we, douse the lights a bit because the tail disappears otherwise. So this is Comet 12P, Pons Brooks, and I'll say quite a lot more about Comet 12P later. But of course, in terms of atmospheres, John's been talking about Jupiter's atmosphere and persistent cyclones. We've had our own versions of that here for the last, God knows how long. I mean, it seems since really the autumn that we have been under a never-ending stream of low pressure coming in from the Atlantic, which has made observing really troublesome. And I did mention to some people recently that I really need to take up flower arranging, I think, because trying to observe comets is just a nightmare from here. Anyway, I'm sure we've all experienced the same thing. My friend and colleague Dennis Brzezinski, who lives up here, has actually had a lot better luck than we have down in the south of England. In the south of England, it just seems to be never-ending cloud. And I'm just hoping that things will get a little bit better. Anyway, let's start with the sun. The sun has been very active recently. There's been some really nice activity on the sun. So if you're lucky enough to have been able to get a view of it, you'll have seen some big sunspot groups, including this particularly nice one. And here's just a comparison between the full disk white light image from, I think this is from, I can't remember, this is the MDO continuum image. And this is an image taken by David Strange in Salcombe Regis showing that sunspot group. I think many of you may have seen that group recently. It's been a really nice group to follow across the sun. I managed to get quite a nice view of it last weekend when by some miracle the sun came out on Sunday morning and I was actually home to see it. Lots of other really nice pictures of the sun that Lynn sent me, and again, just amazing kind of resolution that people get. So these are monochromatic images by Carl Bauron showing a very nice active region on the sun. And then a nice full disk image as well by Carl showing the various sunspot groups rotating across the solar photosphere. And as David mentioned, there's an eclipse coming up in a little while, and we hope that that activity will continue. So there are some nice sunspot groups to focus cameras on, but also to enliven the partial phases of the eclipse. Here again, a few more of that big group, and then a really nice time lapse here by Alan Halsey of nice prominence. And of course, what do prominences give us? They give us highly charged particles in the solar wind, which can lead to aurorae. And Callum Potter, our director of the Deep Sky section, who now lives up in the very north of Scotland, off the edge of the north of Scotland in Orkney, has got a camera set up that basically is watching for aurorae all the time. And this is one rather nice example of that. Callum did send some video as well, which is really interesting to watch. Some live video taken with a Sony Alpha 7 camera, so you can actually see in real time what the aurora is doing. And pretty much as is always in Orkney, there's a mixture of aurora and very threatening looking clouds flying past very, very quickly. Okay, so the moon. We all love the moon, don't we? The moon is a lovely, fantastic object to observe, and it really is. I mean, lots of interesting stuff on its surface to observe, but it also acts as a really nice thing to occult other objects, whether they be stars or the sun, and of course we wouldn't have total eclipses if it wasn't for the moon. So where are we at the moment? We've just gone past full moon. And the moon also has this amazing effect on the weather. And I don't know what physical connection there is, but generally the only clear skies I've got in the last 6 months have been around the time of full moon, and I have no idea why that is. So we got full moon. There was actually a penumbral eclipse at the last full moon, a very, very tiny penumbral eclipse visible from, it would have been visible from here if it hadn't been cloudy that morning, with the moon very, very low on the horizon. The next new moon, though, is this one, April the 8th, and that's the one corresponding to the total eclipse that's coming up that will be visible across the US, bits of Canada and Mexico. And then later on in the year, we have another lunar eclipse on September the 18th, which is bits of it visible from here, and we have an annular eclipse, that time, annular solar eclipse on October the 2nd. So, yes, the moon is lovely. We kind of have some of us have a love-hate relationship with it. It's a fantastic object to look at in a telescope, and actually when it's low on the horizon, the full moon is a really impressive sight that gets lots of people commenting on it. So Peter Carson actually went out to take some images of this comet, this very faint comet that's over in the northwestern sky. And this was on the 24th of March, which I think many of us actually had a clear sky on the evening of the 24th of March. And Peter sent, whilst he was basically taking pictures of the comet, this is where he was. This is Canewdon Church, which is out towards the marshes in East Essex. It's one of the high points of Essex. I don't know what the altitude of this, 100 foot above sea level or something, maybe 50, something like that. But I joke about the moon, but this image really took my breath away. This is an image of Tycho, large lunar crater, fairly new lunar crater, new in lunar terms, but just amazing resolution by Mike Greenhill-Hooper. And when you actually look at the instrument that was used to take this, it's a 20-inch Dobsonian. Now, in the olden days, Dobsonians used to have kind of a reputation of being light buckets. You know, they collected lots of light, so you could see deep sky objects, but you didn't really care too much about the optical performance. But clearly the optical performance of these obsession Dobs is stunning, and just an amazing image. Really incredible image. I don't know what the resolution of this must be, but it must be down to hundreds of meters, I imagine. Just incredible. Okay, so eclipse. The eclipse is coming up. This is the eclipse of 8th of April. Some of us are lucky enough to be going off to observe it. It basically crosses over, starts here on the west coast of Mexico, crosses over the border across the Rio Grande, and Trump presumably would like to build a wall over here to stop the Umbra actually getting from Mexico into the US. but nothing he can do to stop it. Goes across through the US, basically Texas here, and then into cloudier and cloudier and cloudier bits of the US. Just about visible from Niagara here, misses Toronto just about, goes through Canada, and then finally goes off over, is that Newfoundland? Newfoundland, yeah. Which I discovered as I was putting together the times for this, has a very odd time zone. It's one of the few places in the world that has a time zone offset by half an hour from UTC, which is a little bit confusing. Anyway, here it is. This is a really nice animation of that. The little black spot is the umbra, where all the exciting stuff happens. Then you've got the penumbra, which is the partial eclipse zone. And as I mentioned, really there's kind of two places that a lot of people from the UK are going to see this. One of them is down here in Mexico, near the west coast of Mexico, where in fact this is near to the time of maximum eclipse, which is about 4 minutes, 20 odd seconds or so. The other one, which is rather easier to get to, is as it crosses over into Texas, where in fact it just clips Dallas-Fort Worth. So you could, in theory, fly into Dallas-Fort Worth, get out the plane, wander out a bit, see an eclipse, and then fly back home again. But probably impossible to do that. There's all sorts of stuff going on, because this is not long since the last total eclipse that crossed the US. Lots of people saying, you know, this is going to be the greatest thing of all time, but then there are other people saying, don't look at it, it's too dangerous. You know, during totality, you could be possessed by demons or something by looking at it, so don't do it. So I think we all know that it's dangerous to look at the photosphere of the sun, very, very dangerous. But once the moon has covered that photosphere, so at this point here, where we have the second contact diamond ring, it's perfectly safe to look at the sun during totality. And in fact, if you try and use a filter during this time, you ain't going to see anything at all. And of course, what you do see is the corona, the lovely corona around the sun, the prominences. And you can look at it in binoculars or a large telescope, you know, amazing views if you're lucky enough to do that. But you've just got to be aware that as soon as you see a red band coming out here, which is the chromosphere, a little area above the sun's photosphere, you need to stop using optical aid and then go back to naked eye. And it's perfectly safe to see that third contact diamond ring with the naked eye, because it's coming through a very, very small break in the moon's limb. But when you see that, basically, and once you've seen the diamond ring, just go back to using filters again. So hopefully, and here it is, there's the diamond ring. This was the Australian eclipse back last April, which was only 50-something seconds long. This one coming up is going to get quite boring, because it's going to be totality for 4 minutes or so. And we're not going to know what to do during totality. In terms of the weather prospects, yeah, nobody can predict the weather particularly accurately, but what you can do is you can work on statistics, and the statistics show that actually Mexico's probably got the most likely sort of reasonably good weather prospects. Texas not too bad, and then generally, as you'd expect, it gets a little bit worse as you move north and east as it goes across the States and into Canada. In terms of what's going to be in the sky, potentially quite interesting. You've got the sun in the middle here. You'll have Venus, very, very easy to see, probably 5 to 10 minutes before totality to the right of the sun. Jupiter a little bit more difficult to see, further to the left of the sun, but you'll see that definitely during totality. And then there's another thing, which is the comet that we're currently seeing in the western evening sky, 12P, will be there in the sky during totality. Now, there's been a lot of rubbish written about this, about whether people are going to be able to, you know, have the opportunity to see this comet during totality. Well, the sky brightness, even for this eclipse, which is quite long, the sky brightness in the middle of totality will be something like the brightness of the western sky at the end of civil twilight. And you're trying to see a 4th magnitude fuzzy blob in that bright sky. It's extremely unlikely you'll do it. Possibly with a big pair of binoculars, if you know exactly where you're looking, you might do, but do you really want to spend that time during totality staring at a bit of sky? So probably not. But I would say it should be a lot easier to photograph, and of course you can set up a camera to do that and not actually have to do anything during totality, just leaving the camera running. And I've got an example here. This is from the eclipse of December 2020, when there was a comet called C2020S3, Erasmus, which was about 5th magnitude, so about a magnitude fainter than 12P is, and it was closer to the sun in the sky. And I actually intentionally set up a camera with the objective of taking a picture of this comet. Basically, it's not visible on individual frames. What you have to do is you have to take hundreds of frames during totality of the sky. You have to take very good flat fields. You have to calibrate your frames when you stack them together and then remove the background. And the background here is removed by running what's called a median filter over the image. I can get down to about 7th magnitude stars. And here is a 5th magnitude comet. And you can actually even see a bit of a tail. And what was interesting about this eclipse is completely unknown to us at the time the eclipse was happening. There was another comet, this one, 2020X3, I think it is. Yeah, 2020X3, which was discovered by the SOHO satellite. It's a sun-grazer comet. It didn't survive perihelion. And in fact, you can see it on the screen. It's kind of yellowish. So S3 is green, because all comets are green. X3 is yellow. And the reason X3 is yellow is basically it was being fried by the sun at the point that I took the image, and it was effectively being completely evaporated. So what we're seeing there, that yellow, is probably sodium or something, I guess. Anyway, so the comet 12P will be about a magnitude brighter and further from the sun. So I'm pretty confident we ought to be able to get a photograph of that. And my plan is to use a 50mm camera lens on the back of a standard camera, field of view, and put the sun in one corner and Jupiter will be in the other corner and the comet is there, I think, something like that, or maybe it's there. Anyway, I'll check before the eclipse so that I know where to look. One thing you can do with Solarium is take the atmosphere away, which unfortunately we can't really do in an eclipse. So yeah, there is the comet. If you want to have a go, a partial eclipse is visible from the very extreme western side of the British Isles. So this is actually the view from Cork in the Republic of Ireland on the evening of April the 8th. And here you go, quite a nice partial eclipse, 1 degree above the western horizon. So knowing what the weather's like in the southwest of Ireland, the probability of seeing that is probably pretty low. But if anyone's got a nice pad to go to in Cork on April the 8th, that's an opportunity to do a bit of eclipse watching. So moving away from the eclipse then towards the comet, just starting off in the western twilight sky at the kind of mid-twilight, at the end of civil twilight. At the moment, we've got Jupiter still there, although it's kind of rapidly disappearing. We have Mercury, which has just gone past its greatest elongation, and which is always a challenging object, but low down in the twilight, worth having a look for if you have a clear sky. And we've got my friend 12P comet Pons-Brooks, which is a very interesting comet and which I will bore you with for about the next 10 minutes, but with some fantastic images that we've had submitted to the BAA. Before I do that though, this is a nice picture that Andrew Patterson sent in, where you've got Jupiter up here and Mercury down there. So Mercury definitely worth looking for. And as John said, Chris Hooker's been doing some amazing work on Mercury with sodium passband filters. He's adapted his technique, he's worked hard to improve his technique, and I think he's getting really stunning results now. So the results on Io were impressive, but he started really this whole journey of working in sodium passband with Mercury, because Mercury has a sodium tail too. It's a sodium tail which is basically consists of sodium sputtered off the surface by the sun, solar wind, and that sodium tail is excited by light at the sodium wavelength emitted by the sun. There's one problem with that though, and that is that the sun's atmosphere contains an awful lot of sodium. And so there's a lot of absorption of that particular wavelength in the sun's atmosphere. That's what the sodium D lines we see in the Fraunhofer lines of the sun's atmosphere. And so when Mercury isn't moving relative to the sun, I mean, it goes around the sun, but when it's not moving in or out, essentially all the light that would excite that sodium tail is absorbed in the sun's atmosphere. So the best time to observe this sodium tail is when Mercury has a high relative velocity due relative to the sun. And so Mercury is in an orbit that's quite eccentric, so it moves in and it moves out. And so what you want is a time when Mercury is visible, so it's coming to an elongation that we can actually see it, but is also in the process of moving away or towards the sun, so that essentially the light that would excite the tail has been Doppler shifted by that motion, so that the exact sodium D-line light that's absorbed in the sun's atmosphere is actually shifted off, and you get something near it which excites the tail. And so you can work out when that is, and those times are fairly well known now, and other people have used this to observe the sodium tail of Mercury. But the work that Chris has done, I think, is probably the best images, certainly from this country, that we've seen. So here's an example of it taken March 24th. That evening, you'll see March the 24th quite a lot. It's the one evening in the last few weeks when we've actually had clear sky in the evening. But a really great picture that Chris has taken here, and as John showed, using that on Io as well. So I bought a sodium filter, not as narrow band as Chris's one, to take to the Palmer with me, and I've got some images of the sodium tail, not as good as this. But once you've done the sodium tail of Mercury and the sodium tail of Io, there ain't much left to do. So it's a filter of very limited applicability, but really interesting stuff that Chris is doing. Right, this is just showing what's happening to the planets over the next few months. And you'll notice that at the moment, Venus is over here, and Venus is moving towards superior conjunction, which I think is on June the 5th, June the 6th, something like that-ish. So Venus is quite difficult to see at the moment. It's getting close to the sun, but this is a drawing that Paul made. Again, unfortunately, it looks a lot better on the screen here than it does on the projection screen, so the fine detail has been blown out a little bit. But yeah, Venus is quite a difficult object to observe now, and it will be for quite a while until it moves through superior conjunction and starts coming out in the evening sky, sort of at the end of the year. Okay, on to my main subject for tonight, the comet. This is Comet 12P on the right, picture I took, and on the left is a guest ale that's on in my pub, the Endeavour, at the moment, which I thought was very appropriate for comet observers. If you do find it, it's by the Chelmsford Brewing Company. It's called Under Cascading Skies, but I think that's definitely a comet, a visual representation of a comet. So this comet is very, very low down in the northwest at the moment because it's coming towards perihelion. And this picture by Duncan Hale Sutton, I think, is really good because it shows you where it is. So it's that obvious thing between the two red bars there. But the key thing is it gives you an idea where it is. So you've got effectively, it's in Triangulum. This is M31. This is Andromeda. Triangulum down here, M33 nearby. So it's basically very low down in the northwest. So it's troublesome to get to, not just because it's low down, but because the weather has been awful. But it's been a fascinating comet to observe. This is its light curve. The light curve is a real mess. So, you know, if you're a variable star observer, you would throw up your hands in horror at this. But one of the reasons is that this comet has been undergoing outbursts. And so the reason there's so much scatter is that the magnitude has just jumped up and down quite a lot because of these outbursts. You can see that more clearly if you look. So this is actually estimates of the magnitude, what's called the total magnitude, so the magnitude of the whole coma. You can see it more clearly if you look at the magnitude very close in, just close to the nucleus of the comet. And you can see here very clearly this comet has had a set of outbursts, some of which look pretty periodic. And Richard was the first person to notice that these outbursts were occurring on about a 15-day cadence, something like that. And you can see here, that's almost like clockwork. Then it stopped for a while, then there was another one. As it's actually come in to perihelion, the outbursts have effectively died away. Part of the reason for that is that the comet itself is just getting so much more active, so much more active and brighter, that to have a significant outburst would require a huge amount of energy released now, whereas when the comet was faint, you could have a significant outburst with not so much. We're coming up to perihelion. The outbursts have stopped pretty much. Once we go over the top and the comet goes beyond perihelion, it's only going to be accessible from the southern skies. And 12P has historically, outbursts have been seen on the inbound leg, which is always visible from the northern hemisphere, but they haven't been seen so much on the outbound leg, which is visible from the southern hemisphere. The change this time is that now with access to remote telescopes and the fact that we have a lot more contacts with people in the southern hemisphere, we should get, and I'm hoping that we can continue this light curve using observations from the southern hemisphere to see how the comet behaves as it heads out. And of course, it will have been very strongly heated as it went through perihelion, so it may take it some time before it can sort of recover back and start giving us outburst again. But we'll only find out by observing it. So I'm just going to run through quickly a few pictures of the comet. This is one that I took, which is processed with a particular filter called a Larsen-Sekanina filter, which is designed to show radial features in the comet. And what this shows, and this is over a period of only 20 minutes or so, is there is distinct relative motion in the ion tail. It's called ray folding. Essentially what's happening is that the jets are coming out in the ion tail and they're being pushed back down the comet. And so what you see is that the rays fold back into the line of the tail. From an imager's point of view, what this tells you is that if you try and make a really long stack of something like this, you'll actually blur out the detail in the ion tail. And so now the comet's really bright. The way to get good images is to actually do fairly short stacks and have a look and see if you can see motion. But this is kind of nice demonstration of how much motion there is in that ion tail. Just running through a few more, and these are really nice images. So this is Peter's image from March the 11th. Peter has the advantage, even though he lives in Leon Sea, of having an observatory in the south of Spain. So he's not quite been so affected by the problems that we have been here. This one's Alan 2, I think, yeah, showing the comet on the 13th of March. Again, these are much better if you just go online and have a look on our website than seeing them on the projector here. But really nice tail with an awful lot of detail. This one, Mike Greenhill-Hooper, who you know from the Tycho image. This one is a wide field image of the comet, again showing a really nice details in the tail. And then going to a completely different scale, this is actually Tim Hames's picture of the comet and M32, M31 and M33. So it's kind of in the region of galaxies, and in fact the tail here is stretching up quite a long way to M33, and of course then you have the traditional cloud as well, just to make the image complete. So a lot of people have been sending in images taken with conventional equipment, but what I've been really impressed with, actually, is the fact that people have been able to use these modern smart telescopes now to get images of the comet. And I mean, this one, it doesn't look like too much, but actually it's really impressive to see what you're getting. So this is by Peter Tickner, and it's the Dwarf 2 smart telescope. And basically from his observatory, the comet's now too low down for him to get from the main telescope. So what he did was he took his smart telescope and he propped it up on the roof of the observatory, and he told it to take me a picture of the comet, and off it went, and it did. And you know, I was, when these telescopes were introduced, a bit sniffy about them, about the fact that, well, you know, why would you pay so much money for such a small aperture and a rubbishy camera? But actually, they've now come to the price point where I think they're really quite clever, and I'm not sure I might not buy one. Because, you know, they really are that easy. You plonk them down, get on your phone, and out pops an image. And yes, you don't know how or why or what it is or whatever, but you know, but you know, you do get that achievement of actually getting an image, and hopefully that will then encourage people to. But so I think they're pretty good actually. They're in my sales pitch. David Strange here. This is with a red cat, ASI 533, from the Norman Lockyer. Again, a nice image. Whee! This is mine from the 24th of March, of course, because that was the one clear evening I've got, showing lots of lovely detail in the tail and lots of detail up the tail as well. So this was, again, I can't reach this from my main telescope. This is a telescope at the other end of the garden, propped up, smaller telescope, 90mm aperture, but really worth it for such a lovely comet. And then the most recent image I've got is this one from Dennis Ptaschinski up in Scotland, a bit smaller field of view, but again showing those incredible features in the tail. Very nice comet, definitely worth having a go at imaging it if you can, but it's pretty much, well, I wouldn't say it's gone, but it's going now. It's very, very low in the northwest, so really difficult to get to. And it's certainly, I mean, I've seen some things in the media, you know, go outside, look to the northwest, and you'll see this wonderful comet, this devil comet in the sky. It doesn't work like that. I mean, I can just about see this comet from my garden in binoculars, knowing exactly where to look. Yes, it would be naked eye from a really dark site, but not from where most people live. There are a few other comets, just want to go through quickly. This one, which I've spoken about many times before, Comet 29P, Schwarzmann-Wachmann, and 12P has outbursts, but Schwarzmann-Wachmann is the real king of outbursts. It has loads of outbursts, and because it's in a circular orbit, we can observe it for years and years and years, whereas 12P we're really only seeing for a few years as it comes in and goes out again. There has just been one outburst, and this is a lovely light curve that Richard sent me yesterday. So Mark Phillips up in Edinburgh, the Edinburgh Astronomical Society has got a telescope in Spain that they've been using to observe this comet, and Mark reported this outburst, and other people got on the comet, and you see a really nice light curve here as the comet rises in brightness from about 16.8, something like that, to about 13.7. So a really, really big outburst. And if you look at the number of outbursts that there have been, quite a lot of them, and that's what makes this comet so fascinating. It really is an amazing object. If you're interested in 29P in particular, if you go on the BAA website, Comet website, there's lots of material about it and Richard's theories as to why it does what it does. And this is one of those occasions where as amateurs we've collected loads of data which probably invalidate some of the professional theories about why these outbursts occur, but the professionals are very resistant to abandoning their theories. If you want to know more about that, talk to Richard. He will bore your socks off with it. Another comet, and this is just what may be coming in future. This is the one that I think I spoke about a few times, 2023A3 Shushin-Chan Atlas. This is the comet that was discovered a long way out and which may become a really good object in October. So making predictions about comets is never a good idea, but it's going pretty well so far. So when I last talked about it, we didn't have much data at this point on the light curve, and we were predicting everything from down here. We've now got good data now the comet's come out of conjunction, and it's fitting the light curve really well. So I think there's a reasonable prospect that we will get a bright comet in the first 2 weeks of October, second and third week of October. If we do, this is what it'll look like. This is a chart that Martin Mobley put together for an article in the February The Astronomer magazine, showing it coming out of the western sky, getting higher and higher in the western sky. And if it's as bright as we hope it is, it could be a really nice comet. You know, we never know. Comets are completely unpredictable, but definitely worth kind of thinking about that one. So just a couple of final things. Variable stars, T Corona Borealis. Of course, we're still all waiting with bated breath for the outburst of this star. Hopefully you're observing it at every possible opportunity. And there are multiple ways of doing that. And one of the really interesting ways is to actually use the all-sky cameras that you can get for free from iTelescope. So Mike Harlow's been doing that, and he's been keeping an eye on these. And essentially they're all around the world, so you can keep an eye on T Corona Borealis effectively 24/7 to see it outbursting. Another thing that's going on is that within the meteor observing community, we all have these cameras that look up at the sky to look for meteors. And there are now thousands of these around the world, recording 24/7 the sky. Now, this is my one of my ones, and you can see here, this is looking up, this is Ursa Major over here, this is Arcturus, and then down here is Corona Borealis. So what these cameras do is they produce a frame every 10 seconds or so, which is stored to your disk, and that's to detect meteors. But you can stack these, and in fact, the limiting magnitude of these 10-second frames is about 6 or 7, something like that. So when T Corona Borealis does go off, the one thing we know is that we will have a very, very good record from hundreds of cameras around the world of its rise. The only slight problem is that these cameras are very infrared sensitive. So essentially they're designed that way. And so we will have cameras that don't have kind of V-band response, but they will give us a really impressive record of what happens when TCRB finally goes. And it'll be this year or maybe next year, or maybe the year after. But no, it'll be definitely within the next year or so, won't it? Who knows? Yeah, it's like, keep observing it and we'll find out. Just one other variable star, which is a very well-known variable star. This is Betelgeuse, Alpha Orionis, and a few years ago it had the great dimming, which I think many people will remember. It's now had a little mini dimming, and it's definitely worth keeping an eye on, but it's disappearing now into the western sky, so we won't be able to follow it for probably more than the next month or two before it's gone, but definitely a star to keep an eye on. And then another one, and I just wanted the opportunity to show another Maz-Yunis picture here. This is a nova that's recently been discovered in Ophiuchus, very far south, but Mazin here has got this lovely picture. It's in a very, very busy field. The only thing I would say is he mislabeled the nova, because the nova is this red object here with the blue arrow, and there was a bit of discussion on the BAA about all of this stuff, but it's a lovely image, and Mazin is doing some fantastic work with his remote telescope in Morocco, recording all of these events. Meteors, not much really happening in meteors. We've got 2 showers coming up over the next month, the April Lyrids, which are ruined by the moon, pretty much, and the Eta Aquarids, which are ruined by the fact they're a southern hemisphere shower, so we're not going to see them very much from here. So I just mentioned them for the record, really, but I don't think we're likely to be able to detect them. And then finally, just before we all head to the pub or off back home, I wanted to show this, and I always sneak in some space exploration stuff. I don't know how many of you saw this. This is the Starship EFT launch, but what's amazing about it is it's live video from Starship during atmospheric re-entry from a camera on one of the flaps, which is why it's kind of flapping around. And what you're seeing here, which I think is just incredible, is the ionization from this thing hitting the atmosphere at 7 and a bit kilometers per second. So whatever you think about Starship, whatever you think about SpaceX and Starlink and all that kind of thing, this came back through Starlink. The reason that they could get these images back is that they had Starlink satellites to provide the link. But I just think this is the most incredible piece of video. I mean, it's just science fiction. It really, really is. And I don't think we're far away from actually having Starship working. And we were talking about this earlier on today, about getting new members and new people interested in astronomy. One of the things that got me interested in astronomy when I was a kid was the Apollo missions. And I don't think we're that far off now, having something like this, doing crewed missions to the moon and possibly even Mars. And, you know, whatever you think about the politics and consequences of that, I think it could be a huge boost to people's interest in astronomy. Okay, thank you very much. And some of us will be heading off for a libation in the parcel yard, which is at King's Cross. So if any one of you is interested in joining us, then please do.
Thank you very much, Nick. Excellent talk as usual. I hope to see some of you at the Winchester weekend in April or in Greenock in May. Otherwise, I'll see you all at the next meeting here, which will be the 5th of June. Have a nice evening, and I hope you get some clear skies, and those who are going to the eclipse, good luck to that.